Apples have been falling, stones have been falling since, well, all the time. Well, smart people like Greeks, for example, were watching these falling bodies, and they had no reasonable theory. They said it's natural for the body to fall because it's the natural place for it. They assigned natural place for everything. Water and solid objects, well, is down below, and air up there. So anyway, that's their theory. So it was the genius of Newton who connected the fall of the bodies to the earth. Come to think of it, if you know the laws of motion, then if you see a body accelerating, you look for an agent. Who is the agent who is causing the body to accelerate? What force is acting on it? Now imagine you're in a room and there's a body lying on the floor, and then it starts moving. You'd be surprised what kind of force is acting on it, what kind of invisible agent. You start looking for the agent. That's what Newton did. Well, when you release a body, it starts accelerating down. And what causes that acceleration? And Newton knew that bodies fall vertical downward everywhere on the globe. England had colonized large parts of the earth by that time, and if something unusual happened, like body falling at an angle, Newton would have known. So he knew that bodies fall vertical down everywhere, that is towards the center of the earth. So there must be a force acting on it towards the center of the earth. And who is the agent? It's tough to not think of earth there, earth as the agent. Then Newton also saw the moon going around the earth like everybody else, but only he got to put the acceleration of the moon as he goes around the circular path around the earth as due to a force due to the earth, and then the planets going around the sun. For Newton, the universe is the lab. So he could make out that there must be some force to make those planets go around in circular paths, because it's not natural for bodies to go around circles. They have inertia, they should keep going along a straight line with unchanged magnitude and direction for velocity. So if they're going around a circle, there must be a force acting on them. And if they're going around the sun, there must be a force towards the sun. That the force is proportional to the mass of the body is fairly easy to make out. If you hold a bag full of some grain, well, you have attached to a spring balance, you feel the weight, you note the reading. If you double the amount of grain, assume the bag is very light. The quantity is doubled, the mass is doubled, the force doubles. So it's easy to make out that. Then comes the other part. The force is also proportional to the mass of the other body. It is an interaction between two masses. If this mass is attracted by the earth must be attracted by this body, and the force by this body on the earth must be proportional to the mass of the earth. So he establishes that. Then where does this inverse square law come about? Newton knew about the third law of Kepler. Square of time taken by the planet to go around the sun is proportional to the cube of the average distance from the sun. This is Kepler's third law. Now, let's assume circular orbits for simplicity, and t would be 2 pi by omega, where omega is the angular speed. So this is t squared is proportional to 1 by omega squared, or omega squared is proportional to 1 by r cubed. R omega squared is centripetal acceleration. That is proportional to 1 by r squared. R omega squared is centripetal acceleration, and mr omega squared will be the force on the planet, and that's proportional to 1 by r squared, m being the mass of the planet. That's a constant for it. So you establish that, the force is inversely proportional to square of distance, and for Newton, the universe is the lab. This is not the result of an experiment done in the laboratory by observations made of forces at different distances and then concluding this. This is from That's what is special about this law. So the force is proportional to the product of masses and proportional to inverse to square of distance. That's the law of gravity, or F equals G m1 m2 by d squared, where G is the universal gravitational constant. And this G is, has a very low value, 6.67 into 10 power minus 11 mks units. And well, I'm happy with this gravity, in the sense that if, say, this were 10 times greater, say 10 power minus 10 there, well, imagine you are lying down on the bed in the night, and then in the night time somehow, well, we just like to imagine these hypothetical cases, the gravitational constant goes up 10 times. The moment you step out of the bed and put your foot on the floor, you'll feel 10 times greater weight. That will be enormous. Your bones may not be able to support you. And if it were, say, 10 or 100 times weaker, well, that is, this was 10 power minus 13 instead, you'd feel very light. Your strides become very long. And if somebody gives you a push, you would just easily fly away. It will be tough to stay at one place if you are very, very light. Anyway, we are happy to be living in the gravitational field we have. Our biological systems have evolved in this on this planet, and if you came into existence on some other planet, you would have perhaps evolved differently. But I'm just saying, if you go from here to some other planet, well, where the gravity is either 100 times stronger or 100 times weaker, you would really have a problem. Also, there is one other nice observation of Newton. In fact, he sees a similarity between the falling body and moon going around the earth. The falling body, the force in the falling body is making it change the magnitude of velocity. The force in the moon is making him go around the earth, that is, change the direction of velocity. What if the force that's acting on the falling body, on the earth, the stone, made it go round the earth? Newton draws actually a picture of a cannon mounted on placed on a mountain top and firing a shot horizontally. And if that shot is fired at 8 km per second, the shot would go round the earth in a circular path. What is special about that 8 km per second? Well, at that speed, the acceleration, 8 km per second, 8,000 into 8,000, v squared by r, 64, well, 3 zeros. This is the radius of the earth. This is 10 meter per second squared. I am approximating this 8 km per second just to make the calculation easy. But the idea is that, well, the acceleration, instead of being causing the change in magnitude of velocity, it will cause the change in direction of velocity if it is fired at horizontally at 8 km per second. Newton also knew that a body projected horizontally falls roughly by 5 meters as it in 1 second. In 1 second, it travels whatever horizontal distance it travels. Let's say if it's projected at 8 km per second, it will travel 8 km horizontally and fall 5 meters vertically. Interestingly, because of the curvature of the earth, Earth's surface also falls by 5 meters for every 8 kilometers. If you travel along the surface of the earth, because of the curvature of the earth, Earth's surface falls by 5 meters for every 8 kilometers. So you project something horizontally at 8 kilometers per second. As it travels 8 kilometers in 1 second, because of its speed, it will fall by 5 meters due to gravity. Earth's surface also would have fallen by 5 meters due to gravity, and the body remains on the same distance from the earth. That's interesting, right? So the fall of the surface of the earth by 5 meters when you travel 8 kilometers along the surface needs some elaboration. Consider this situation. This is the earth with the center at, say, O. We're talking of a circle that's drawn with the center of the earth as its center. not say a circle running east-west like a latitudinal circle. When somebody is at a point A, and consider another point, say B. Well, this angle is say theta. Drop a perpendicular onto AO from B, say at C. Now the length of AC would be AO, that's R, and this is OC will be R cos theta. This angle is theta, OB is R, so that's R cos theta. So this is R into 1 minus cos theta. So if you draw a horizontal at A, point B is this much below that horizontal. Take an extreme case of theta equals pi by 2. So if you are here, cos theta would be 0 for theta equals pi by 2. You would be R below that horizontal. But we are interested in AB equal to L. Say that distance is L. AB, if that's 8 kilometer, what happens? So that angle theta in radian would be arc length L by radius R. And if this is 8 kilometer, Earth radius is 6,400 kilometer. This is 1 by 800. These are kilometer, so this is so many radian. This is 0.00125 radian. If you substitute this value of theta here, well, this value comes to about 5 meter. We are approximating here. You must have heard, like, if a ship is sailing towards the shore, you don't see the entire ship all at once. Imagine your powerful binoculars, and again imagine the ship is traveling along a circle with center of the earth as its center. And there are powerful lights on the mast of the ship spaced 5 meter apart. As the ship approaches you, you see the topmost light first. When it moves 8 kilometers closer, you see the light which is 5 meter below it. So as it keeps on approaching the shore, you see lights one after the other. As it approaches 8 kilometers, you will see light which is 5 meter below. So anyway, that's about fall of 5 meter when you travel 8 kilometers along the surface of the earth. Couple more things about the law of universal gravitation. It's called the law of universal gravitation. Universal because, well, this is valid for small masses, large masses, small distances, very large distances, like distance between planets and the sun. There's no law that was established in the law which could be applied to bodies at all distances. Well, that is, at least it is not certain that the laws that were established in the lab would work for everything around in the universe. So this is called law of universal gravitation. And also Cavendish actually did an experiment in the lab to verify the law of Newton, and this was after the law was normally laws are the result of observations made in the lab, but this time around the law came from elsewhere and experimentally it was verified by Cavendish. Also, another thing that you need to know is that if a small body is in the neighborhood of the earth, on the surface of the earth, it is pulled by every mass element of the earth, all mass elements. For example, a mass element here pulls it in that direction, a mass element here pulls it in this direction. Newton establishes, by doing a lot of math, that the earth's mass can be assumed to be at the center of the earth for the purpose of calculating the force of attraction between the earth and a body on the surface. So mass of the earth can be assumed to be considered at the center of the earth for the purpose of the calculation. This is because the law is inverse square law. Had it been inverse cube law or something, it would have been a different story. Mass cannot then be assumed to be considered at the center of the earth. So it's inverse square law. That's nice for us. And the sphere's mass can be assumed to be at the center of the sphere for the purpose of doing calculations of force on any object and the sphere. This object, of course, being outside the earth. If you are somewhere here, well, you'll be pulled in backward, forward in all directions. Whereas here, the pulls are all towards the center, have components towards center. Right? If you're right at the center, if you imagine a hypothetical situation of being right at the center, you'll be pulled in all directions and the force should add up to 0.